Hello and welcome. Here we are in lecture 7. So, uh, we're churning along full steam, right? We're doing more and more cool, fun things in Chisel, taking advantage of Scala, building up more abstractions, getting more productive. Um, and some of the things that comes up when you start doing that is you actually don't just have one module, you have multiple modules, right? And then you start talking to each other, interacting with each other. And what we're talking about today is, well, how do we make those modules perhaps more decoupled? And by making them more decoupled, it makes them easier to reuse them and interoperate. We're going to cover a few things. We're going to cover decoupling. Before we do that, we're going to cover something called a case class. It's another Scala feature. Like I said, over the course of this quarter, you're going to learn a lot about classes and object-oriented programming. And so case class is yet another thing we're going to be using. And then we're going to conclude by actually playing around quite a bit with the queue provided by the Chisel Standard Library. Okay, so as I mentioned, the whole point for decoupling is you want to have time sensitivity, right? So let's be clear what we mean by that, right? Normally, if you have hardware components, right, they aren't just, need to be connected physically with wires or something. They also need to agree upon, what signals mean what things at what times, right? Not just what the values of signals are, right? In software, the API is enough, right? In software, you can just say, oh, well, I have this function call, and if you call this function, I will do the following things for you. In hardware, the time also is part of the contract, right? You send signals at certain times and you expect responses at certain times, right? And that can be really brittle, right? To get it exactly right, be really clear what that is. And so an alternative to that is a decoupled design where you actually say, you know what, rather than being so tightly coupled, I'm going to say, here's my request, and then you're going to handle it when you handle it. And so there's some flexibility for the responder to take more time. If you do this correctly, it takes no additional time, but it has the flexibility in the future. If you need to take more time, you can, right? But why we're excited about the productive hardware technique is, if you do this correctly, you can make both components a lot simpler, right? Rather than kind of bake in a lot of assumptions and requirements about timing interactions, we can have a decoupled interface. And when things are decoupled, they're way more reusable, right? Because that way you can use in one context of one set of timing constraints, use in different contexts of different set of timing constraints. And so you want to have decoupled components. It's a good thing to do. Okay, so go ahead and load up our notebook. And I just motivated decoupling. We're going to have that brief aside into Scala case classes, right? So what is a case class? It's a special kind of class that has a lot of features built in. Many things you can do with case classes, you can do with regular classes. It just takes a lot more code. And so case classes kind of cover a very common case where, no pun intended, but a lot of scenarios can be covered by case classes, right? And so what's nice about them is you declare it once. Let's say like down here, case class movie. And maybe initially we will not even have the function, right? So at this point, it's just basically like declaring a struct, right? Now what's cool about it is that, by default, everything's all immutable and public. So it's completely okay for us to, declare a movie. And then, we can read one of the fields. With regular classes, you got to say things are val. Here, case class, you don't need to worry about that. You can easily grab the values. You can kind of declare them nice and concisely. Additionally, you can copy them, right? So normally when we had classes before, everything's immutable. You're like, oh, well, I like that, but I want maybe a different version of that. With the case class, implements this .copy method. And with .copy, you can simply overwrite the fields you want to change, and otherwise keep everything the same. If you want to overwrite nothing, that's also okay. And it's really helpful, right? You may notice, for example, here in our interactions, this is very human readable, right? As you've seen previously in previous lectures, right? If you have a random class and you instantiate it, it'll print out, the object type and then, some fraction of its address, right? That's not very instructive. You can implement a toString method, so that way, when you're printing it, it'll give you something. Case classes do that automatically. Case classes already have this stuff, right? They already have the two strings. They already have copy. They also have equals. So if you want to compare them, that works totally great. Normally, with class instances, right, if you compare to what you think are instances, you're actually comparing two references, right? So it can tell you it's the same reference or not the same reference. This will actually compare by the value, right, the actual data, which is probably what you want. So for a lot of things, they're really freaking helpful. Later on in this course, we'll cover something called pattern matching, also really helpful. And so all the things I discussed, or if these case classes were just simply data containers, right? But they aren't simply data containers. You can put methods on them, right? So in this case, we have this trivial example using movies. We can, decide to take the year and turn it into a decade. Sure, no problem. We can add a function to our case class. And so the reason why we're covering case classes in this course is in your chisel designs, they're a really great way to hold parameters. Or if you have parameters for your design, so far we've had these kind of trivial parameters of, something like a bit width or something, but eventually you start having really big designs and you end up with a lot of parameters. A case class is a way to kind of nicely encapsulate all of them, right? You don't have to have, a really long constructor list for your generator because you want to have a lot of parameters. No, you can just take in a case class and hold the parameters, and that can have a lot of fields inside of it. You can easily match on them, change them, copy them, etc. Cool. Questions so far? So let's take our, counterexample we've been working on for a while and just, originally we just had a limit. Maybe now we'll say we'll have a limit and even a starting point. Check this into a case class. Also notice that while we're at it, we might as well figure out the bit width now, right? So we did the whole trick about figuring the bit width and the limit, adding 1, log 2, we understand that. Here's the cool thing. Now our actual generator description, we can simply say, hey, take these parameters, which happens to be, this case class. Using them is pretty straightforward, right? We can, get the fields out we need to get. So we can take the initial value, we can take the width, and yeah, we're off and rolling, right? And of course, we can print the Verilog, but we know what it's going to say. But yeah, so this is pretty cool, right? We've encapsulated parameters. We actually even did some interesting computation on top of them. And now our generator is a little bit tidier. And also, if someone trying to call it, it can be a lot simpler. In this case, we even have, a parameter which is, optional. So it's a default value. And yeah, that works well. In this case, they want a max value of 14. That's fine. Let's say they actually want to have a certain, starting value. Then yeah, it'll actually have, 5 go in there on reset. If that's something you wanted. Yes. What kind of overhead are you talking about? To be honest, I'm not as expert under the hood for Scala, so I can't promise there's not, some slight, runtime overhead, a few more Java bytecodes, but I can tell you performance-wise, this should be fine, right? Uh, you know, um, I don't think there'll be much of a penalty for having a case class here versus having 2 or 3 arguments coming in. That should probably be comparable. Yes, there'll be the time it takes to construct the object and stuff. There's some time there, but that's going to be dwarfed by the time actually generating the hardware and doing all the hardware stuff. So it's worth appreciating how even a design this small and it seems to run, in a few seconds or less, uh, there's actually so many passes the internals do over your hardware design, making it realistic and making sure it's safe. And so there's quite a bit of computation. So if you're adding constant time computation to your generator, that's usually not going to be too bad. Cool. Other questions? Okay, so this is, yes. Type what? Can you narrate that example again? So you want, okay. Oh, yeah. Let's find out. That's like a tuple converting to a case class. I don't think so, right? So it's finding a tuple, and yes, it needs to be a case class. Now, what's interesting is there's something called mixins. So it's a really cool technology inside Scala where you can basically there's a way you could do this where it would work out. That's how notice how we do things like 1.u. So one is of the original Scala class int. Chisel wants a uint, and how to do this conversion? Well, it seems like we somehow made a conversion from int to uint by modifying the int class. But int class is part of the standard library. We're not allowed to modify that. And so using mixins, they're able to do this. And so I'm sure you can do something similar with mixins where you could have this implicit conversion between a tuple and a case class, but it appears like it's not there by default. It's an interesting question, yeah. And when we start doing pattern matching in a week or two, You'll see some pretty cool stuff with case class you can do with pattern matching. And I'm sure there might be a place to also come back to this issue of what if you had implicit cast to tuples and that kind of stuff. Yeah. It's not quite that sophisticated usually, but you can do some pretty cool stuff with it. Um, yeah, we'll see in a week or two. Cool. Okay, so I said case class. We understand it. We're going to file it that way. You're going to see that in the labs and homeworks. It's useful. From now on, usually our parameters will be a case class. That's kind of handy, etc. Okay, back to the main event of decoupling. So like I said, you have two hardware blocks, um, and now we want to figure out how to make them interact, right? And as I said in the slide, right, even getting one sequential block correct sometimes is non-trivial, right? As you've seen this course in just the first two homeworks, homework one was purely combinational. So once you wrapped your head around Chisel and what you were being asked to do for homework, most people find that problem pretty easy. Homework two's problems, and now we have registers in the mix. Even though designs aren't that complicated, there's now a lot more possibilities for things to go slightly wrong, and there's a lot more debugging, a lot more questions. That's normal. That's natural, right? Sequential design is harder than purely combinational design. And guess what? If you have multiple components, they're sequential components, and they're interacting, that's harder still, right? And that's not just harder still, it's unfortunately also the reality of having any non-trivial design. And so let's simplify for now and just say we're having one-way communication, right? Often modules talk in both ways or multiple ways, but let's just say for now we have two modules, one's a producer producing data being sent to the consumer, right? And so something as simple as just transferring data from one module to another sounds really simple. However, we need to recognize some cases that come up, right? In particular, recognizing that the producer isn't producing data every cycle, right? This is the timing issue we were talking about in hardware earlier. And the consumer is not able to receive data every cycle. And so how do we do that in kind of a disciplined and rigorous way is kind of the question, right? When it comes to this data transfer, if you think about this is now being a bit more philosophical. This is actually a really pervasive problem throughout all of computing. It's not just hardware design. When you have control, whether it be in this case controlling low-level hardware gates and hardware, this actually comes up even at the cloud scale when you have multiple servers trying to interact together, or all sorts of things in between. There's kind of this notion of having centralized versus distributed control, right? Like where does this coordination come from, right? So centralized, of course, you have singlet C that sees everything. It's kind of all-seeing, all-knowing, all-powerful. It can often be more efficient, right? If you can see everything at once, you understand what's going on, you know exactly where it needs to go. You can see, oh yes, this data is available, this data is needed. I can send it right over right away. So in that way, it seems more and more appealing, right? So why do we use distributed? Well, guess what? Centralized stuff doesn't always scale, right? At some point, something is too big or information cannot be brought to one place. Those decisions can't be made centrally. It needs to move to distributed control, right? Where distributed, you have independent entities and they only have partial information, you only know the local information. So they need to come to convergence and communicate with other entities to figure out what happens, right? So peer-to-peer. And so it turns out throughout systems, they said at the cloud scale, even low-level in hardware, this tension emerged between this centralized and distributed control. And what's interesting is people go through this, there's various, techniques and approaches and different scenarios. The same conclusion usually kind of emerges. And that is that for small things, centralized is better. There's a certain amount of overhead and complexity to doing distributed. And if you can get biocentralized, things will be more efficient and simpler. However, there's some scale at which centralized will not scale as well as distributed, and distributed will become actually the simpler one at some point. And so as a result, you actually end up having both. You have both centralized and distributed. The question is just at what scale do you decide, I'm switching from centralized to distributed. So this long rant is over. Now bringing this back to hardware design, same thing, right? Within your module, you might have centralized control, or you might have, all the logic inside your module is all there. It's all clearly laid out. You know what's going on. You're the one designing the module. This module is going to be instantiated, all at once, and so it's all going to be all there. However, between modules or even between larger components, you might need to have some sort of decoupling, distributed, et cetera, right? In the case of today, we're talking about communication. We want for things that's like, for producers to say, you know what? I don't have data to send this cycle, right? I do other cycles, but this cycle I'm not sending data. So what's on a wire? That's garbage. Ignore it, right? Alternatively, for the consumer, you will say, hey, I'm busy. The data you just gave me takes a long time to compute that. I can't always do it, right? Because you will apply back pressure and say, I can't take data. So I said, having this makes communication systems much better. Because otherwise, you can imagine for both sides, it's a lot of work, right? If you didn't have these two abilities, the producer is required to make useful data every freaking cycle, which are some applications maybe there's not useful data, so you're just giving somebody busy work, so to speak. Meanwhile, the consumer needs to be ready to handle data every cycle, and maybe that's also not required. Maybe like some things take more effort to implement, and to actually have that ability costs you quite a bit. So having a communication paradigm where we can indicate we're not sending data or choose to not receive data is really, really helpful. Cool. So this brings us to the ready valid protocol, which you've probably seen in a hardware design course, but we're going to cover it here. So the idea is we're sending data from the producer to the consumer. So the data we're sending is the bits. This is perhaps a bus with multiple bits. And there's these two one-bit signals to control it. There's the valid signal going from the producer to the consumer, and the ready signal going backwards. So the valid signal is set to 1 on the cycle in which the producer is ready to transmit data and data is on the wire. However, just because the producer is ready, it doesn't mean the consumer is accepting it. So data is only accepted by the consumer when the consumer says they're ready. And this is 1. So the result, because you need both parties to agree, data is only sent when both ready and valid are true in the same cycle. And if they're both true in the same cycle, the data at that cycle is what actually gets sent. And so this gives both sides the flexibility they want, right? It allows the producer to indicate, you know what, I am or I'm not sending data right now. And it gives the consumer the ability to recognize, hey, I'm not ready for data right now. Please don't give me data. And like I said, even though there's these one-bit wires that are saying their intention, they are aware of what the other is doing, right? For example, I can be trying to send data, but if I know the consumer is not taking it, I'm not going to advance my data. Right? I'm going to keep the same data I'm trying to send and wait till they're actually ready to take it. Likewise, for the consumer, even if I'm ready, if they're not sending me data, I shouldn't process it, right? And so, as an example, a little waveform, imagine initially ready and valid are 0. So ready and valid are 0, no data is being transferred. What's actually on bits is a don't care, right? We actually don't care what's there. It could be anything because nobody's looking at it. Now, let's say the producer is ready to send. So valid is set to 1. And they put some real data on the wire. Even though there's real data on the wire and it's valid, it's not actually being received because the consumer was not ready, right? Another cycle, the consumer says they are ready. So at which point, you have both ready and valid true in the same cycle. So then the data is actually sent. The producer knows the data was sent. They know that ready was true, same time they had valid was true. So the result, they now move on to their next data element, right? Whatever perhaps it's data 1. And they can send it. And then you can see eventually, you know what, maybe they only want to send 2 elements and they're done. So they turn off valid and now no more data gets sent. And then whatever's on the bus doesn't matter anymore. Cool. Questions about the ready valid protocol? Like I said, there's all sorts of subtle variations. This is very common in hardware design. Yes? This is used for data communication. Can you explain the power implications maybe? Sure. Um, so to answer the question of how this relates to power gating, right? You can imagine scenarios where maybe at a very high level, some block recognizes idleness, it turns itself off, and because it knows most of itself is turned off, it will choose not to turn on ready until it's turned back on. That could be possible, right? So power gating is kind of orthogonal to this, right? This is a protocol you can build to communicate data. You can imagine the reason why one entity is perhaps not ready to receive is perhaps it's put itself into a sleep state or even power gated itself, and then needs to be woken back up. But this is just a way to agree, are we actually sending data? Like I said, this is such a simple problem, right? We're just trying to get data from box 1 to box 2, and yet we need 3 wires, right? Because we want to make sure everybody agrees, okay, I'm sending data, you're receiving data, okay, data is sent. Um, yes? So what was the iteration you wanted? Oh, okay, yeah, so good question. So the question was, yeah, so in reference to some of the alternatives to ready valid signaling, perhaps some that, does the ready or valid a cycle beforehand. That is not baked into the standard library. The standard library is only this particular flavor. So yeah, that's right. So some people really stress out about um, is the ready valid the same cycle or the cycle before, and that can sometimes get you some clock, improvement for critical path. You'd be surprised how careful design, even with this constraint of being the same cycle, you should get this right. Yeah, there's IP out there in Chisel for Axie, but I don't believe Axie is in the standard library. But there is Chisel IP on the web for Axie, and this is the kind of thing where you're asking great questions. What if you became convinced you had a better handshaking methodology that was perhaps either more gate efficient or more timing path efficient, and you wanted to make that? You can make that. That's what's cool about Chisel, right? You can just write it and then share it, and boom. Like, you want to change Verilog with Verilog tools, it's not really something that's easy to do, but you can make your own Scala library, bit it in there. You don't necessarily even need to fork to Chisel. You can often do a lot of things on top of Chisel in the Scala level as the program on top of it and does the right thing. So yeah, so that'd be fun. So maybe it's something people can consider for a project end of the quarter is, okay, what if you want to do your own time methodologies and make it the Chisel library or something? It might be something to consider. Cool. So as we just discussed, right, this is in the standard library, right? And all you can do is manually. If you're doing ready valid signaling, I really encourage you to do that with the standard library, right? As we say throughout the quarter, right? When things are in the standard library, if what you're trying to do is in the library, use the library, right? That's less code for you to write. Because you're not writing this code, there's less chance of you writing an error doing that. It's more standardized. And improves readability, right? Someone else, they know the standard library, they'll see this code and know exactly what it's doing, versus if you write your own version of the same thing in the standard library, they got to spend some time to realize, oh man, this person reinvented the wheel and I got to understand their new wheel, right? And so we'll see some examples, but it's really pretty straightforward, right? It's like you just declare a signal as either valid or decoupled, and you wrap it and you get the support, you get some helper functions. By default, these things are all in the output direction. So oftentimes you might call flipped on one of them and make it the input for something, but that's a simple trick. And so actually there's two things here. So what I covered on the prior slide is decoupled, where it's ready and valid, right? Where you send data when ready and valid is true. This handles a lot of cases. So this is a case where, because there's that ready signal, if the consumer is not ready, they can say, hey, I'm not ready, ready is false. And as a result, they can apply back pressure and the data transaction does not happen. Valid as a protocol is much simpler. It's just a valid. So there's no race signal because the race signal is assumed to be always one, right? So basically, just a way for a producer to say, I'm actually sending data or I'm not sending data. And it's assumed that the consumer can take it no matter what. And so in some ways, I think it's almost like the Scala option covered before, right? So Scala option is a way to say, hey, I have this, object, it might actually be real data or it might be empty. It might be none. This is kind of hardware equivalent of that, where you're saying, you know what, I have real data going on this wire this cycle, but maybe later on it won't be real data, and I'll tell you that by showing you the spit to indicate what it is. So these are kind of two flavors. And of course, if you're curious, you always can, click on the links to go get to the API docs, which is going to load hopefully in a second. There it is. Now, one thing that comes up, if you use the decoupled one, is that sometimes when you have these ready and valid signals, even though you're outputting one of them on one side, for example, the producer outputs the valid signal, you actually care about the nature of the ready signal, right? For example, in the prior slide, right, you want to know both were true, so you know to advance the data you're sending. One thing that can come up if you're not careful is if both sides combinationally depend on the other side, you can make a combinational loop, right? And this is something to be careful of. For those of you familiar with this kind of situation, realize that it takes two to have a combinational loop, right? So if only one side does this, let's say producer produces valid and looks at ready at the same time, and there's a combinational path from ready to valid, it's actually not that bad. Because there's only one side, right? Now, if the consumer does the exact same thing, then both sides have done it. Now you have the combinational loop. As a general design principle, to make your decoupled protocols nice, you should not depend on it, because that you don't know who you're talking to, right? And so if you don't have that link, then that way your consumer won't have that problem, right? But if only one side does it, as soon as the other side does it, the tools will immediately yell at you. It's not quite a case of, oh, there's a combination loop there, but I didn't find it. Can I have the right data to animate it? No, no, no. At elaboration time, the tools are going to say you made a combination loop and warn you, right? But like I said, if you can avoid doing this, your module is more reusable because that way the other side, if they want to make the combination loop, they can, but it won't be your fault, it'll be their fault. So keep that in mind. Cool. Questions so far? Yes, yes. You can stick a flip-flop in there, all sorts of things you can do. Like I said, the common thing that comes up, like I said, is that if you can generate valid in some manner, it's not that you can't depend on ready. It's just that you can't be a combinational path from ready to valid. And if there is a combinational path from ready to valid, there should also be a combinational path from valid to ready, right? But yeah, so if you can produce valid from some combinational flops or internal state that does not directly combinationally touch ready, you're fine. Yeah. So it's pretty lightweight actually. If you go peek at the code, um, it's really just uh, a wrapper that gives us some helper functions we're going to see in a second. So it's going to add some the extra IO signals for us, and it's going to give us some helper functions. It's not doing anything more than that. There's not a whole lot of hardware added other than the additional wire, um, which is what we wanted, right? So it maybe helps us see an example, right? Before we see an example, for those who are maybe not familiar with combination loops, I'll give a primer on that. So combination loop is hardware where you have a feedback path that does not go through a register, right? And the reason why this is problematic is it's not always clear how the hardware is going to shake out on this, right? So for example, let's say they had an adder and they wanted to build an accumulator, or in this case, actually even a counter, right? And I just attach the output to the input of the adder. What's that going to be, right? As a solver person, you're like, oh, well, sure, it'll like add one, add one, add one, add one. But there's nothing having that be nicely synchronized, right? There's nothing there to regulate that for register. And so as a result, this is a combinational loop. And, in the common case, you usually don't make useful hardware. Sometimes if you do it exactly right and exactly the right logic functions, it can converge and this is useful. But that's usually not what you want to do. And as a result, the tools even tell you you did this, right? So I tried to write this loopy counter. It's going to be like, whoa, 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 you have a combination loop detected, right? And even tells us what's in the cycle. These are, of course, the underlying terms you'll see in the Verilog. And the solution, of course, is put a register in there. Oops, and then it's going to, be just fine. But yeah, so you generally want to avoid combinational loops. And so the tools will yell at you. And like I said, when it comes to ready valid signaling, everybody's going to smile and nod today. And then in a week, when the homework, you're going to keep pulling your hair out. Like I said, just take a deep breath, look at your design, and realize that it may not be obvious. It may go through multiple modules. It may go through your state machine. But if there's a combinational path from here to here and from here to here, you're going to have a combinational loop. And so as long as you break up one of those, you're good. Cool. Okay. So then, given that, let's go ahead and use valid. So this simple example, we have a module which takes in two things, a single bit enable and an input, and it's going to pass it out, but it's going to now, formalize this into the make valid protocol. And so basically, as by virtue of calling valid on this out actually now becomes two things. It becomes dot valid and dot bits. So as you can see, the dot valid is a single bit wire. The bits is however big the original type is, right? And so we can connect both of them. And we've done that in this case, and so sure, now our enable is controlling the valid and the bits get passed through this module. But that's an initial example like that. Cool. So let's go ahead and advance. Now, that was the sender. What about the receiver, right? Well, the receiver is going to take an input. And like I said, by default, valid and decouple are in the output direction. So to make it the input direction, we're going to call it, flipped. And then what does this module do? Well, this is only for simulation. It's not going to be useful in hardware. But hey, if we ever see something that's coming in that's actually being sent, we'll say we received it. And then in this tiny little test bench here, we're just going to simply just poke the cycle number into the original module. And then for fun, we're going to say it's a valid only if it's even. So let's go ahead and run that, right? And you can see that, right? As we go through cycle 0, we send 0, and we say it's valid because 0, mod 2 is 0. And the other says, hey, I got it, it's valid. The next cycle, cycle 1, we're sending cycle 1, but the first module is not setting the valid signal because the enable's not high. And so as a result, um, it's going to be doing that. Actually, wait, I can actually, yeah, and so you can see it's kind of going through that case. And as you see, only on the even cycles when valid is true are we actually receiving this, right? So we've accomplished our goal, right? That basically, in this trivial example, we decided arbitrarily that, you know, the only time we really want to send data is when it's an even number, and the other times we're not sending it, and the other end can correctly detect that, right? Looking at this valid signal, in this case, using a when statement, they can recognize, oh yeah, this is the correct data or not correct data. Yeah, okay, great. More questions? Yes. Oh, how is the Verilog? So it's not. So the Verilog in this case is less so about the valid and more about the the when, and the when's going to be a mux. This one has the initialization, but if we go digging into this more, oops, not that much. One click, I think, right? Oops, there's a way to get this to. We'll zoom out. Um, yeah, I mean, we can see that part of what's going on is that this is a non-synthesizable construct. That's why there's all this stuff for the printf. But basically, you can see for the printf, right, it's going to do the thing we want if it's valid. And it's technically not under reset. If we were doing reset, it's actually not would print. But yeah, like I said, the when is same when as before. This is just a 1-bit bool. The 1-bit bool was created by this valid construct. Cool. Another question. Dot otherwise. So in this case, the bits is not coming from here. It's coming from here. So let's try what you're proposing, and I think it's going to yell at us. But let's confirm that. So basically, the bits is coming from here. Actually, I'm not sure I'll do what you're describing because the issue is, let's say I don't ever set that. I guess it's going to turn out to be 0. Okay, that's surprising. Hmm. Yeah, so if you're using whens to assign an output to something, and there's a path through the whens that leaves the thing unspecified, it will error. Yeah, it'll tell you that this thing has an unspecified condition. Yeah, so you have whens, you can have otherwise. Alternatively, you can use the last connect semantics and give like a default value and say like, x connected to 2, and sometimes overwrite it with the when. Well, yeah, so remember in this case, because we flipped, both in general is a input, right? And so both valid and bits are inputs in this case. And our test bench is the one that's actually poking them. But if we go back a slide, right, what if I, try to be picky and say, oh, well, you know what? Why don't we, you know, do this only when uh, this is, enabled? It's going to yell at us, right? Because it's not fully initialized. Cool. Other questions? Okay. So yeah, so validate that we're just adding another wire next to the original data to indicate this is, real data or not real data. Um, oops, get our zoom appropriate again. Um, then the coupled, of course, adds both valid and ready. So we're going to do a counter in this case, right? So we're actually using the Chill Center library counter, sure. and we are going to, actually count when um, it's being requested. In this case, we have an input enable for the counter itself, um, and then our output is being received by somebody, not shown, and they have the ability to say they're not ready, right? And so we're only going to count when our input's enabled and our output's ready to receive it. So yeah, we can print the Verilog for this. You can see, there's an advanced counter which has this and condition we were describing. Um, and there's not really any overhead to this, right? It's because we already had this handshaking anyways. It's just by using decoupled, this spares from having to write, out bits, out ready, out valid, in like 3 different lines, right? This is all kind of tidy and combined together. And the second one shows some more critical advantages. For now, you can think of it as just a more disciplined way of writing this. Rather than having a bunch of, signals in your IOs and then a signal comma valid or a signal underscore, ready, it's just, you just say out, oh yeah, it's decoupled, or out, it's valid, and then, it does the right thing. Cool. Other questions? Um, as promised, let's go ahead and um, use some of these helper functions, right? And so what's fun about these is these make the hardware seem higher level. But what's interesting is now that we've learned enough about Scala and Chisel, in a moment we're actually look at the implementation of these functions, and we'll see that they actually aren't anything too crazy. And you might do similar things in your own designs as a way to kind of have more structure to your design. These are, as people in the rest always say, zero cost abstractions, right? These are things we're doing to make our code cleaner and more organized, but there's zero cost in generated hardware. And so we'll see a few of these, right? So for example, ready valid signaling. When is data actually sent? Well, we say as a fire scenario when, both ready and valid. Or for example, let's say you want to send data. Rather than having to attach the data to the bits and set valid to true, you can just say, hey, enqueue this data. If you're not ready to send data, you can say no enqueue. And then on the receiver, same thing. You can say dequeue when you're ready to receive data, or no dequeue if you have no data not able to receive. So here's that same counter example from before. Actually, let's go back to the original one, I guess, maybe. And so originally we said, you know what, we're just going to say count and attach it straight through. But now if we actually make it more sophisticated, um, if we're actually enabled, we would normally need to say, oh yeah, hey, the bits actually is the count, and we're actually sending valid data. If we're not able to send data, we would normally need to say, you know what, the bits are don't care. You don't have to do that, but you could. The prior example just hardwired that value, right? And then you also say the valid makes it really important. You say this is not valid data, it's false. Here we are using the semantics from these helper functions. So we can say, hey, I want to enqueue that data. And hey, I want to do no enqueue. And yeah, this produces, reasonable Verilog. If you're looking at actually, in this case, the tester interaction, like before, we're only going to count on even cycles. And so you can see the count only advancing on even cycles due to this handshaking protocol, where the ability to count is being controlled by the ready signal, which is being controlled by, in this case, whether or not it's odd. I'm sorry, I got it wrong. In this case it's odd, but same general idea. But the key thing for this slide is more over here, right? Where using these high level features like .enqueue, simplifying our code, right? And it's not just the fact this is 1 line instead of 2 lines. It's this is less lines you're writing, less things to get wrong. With someone reading this is faster, more clear what's going on. They understand immediately. Glancing at this, oh yes, you're using a couple interface and you're doing an enqueue. This is not a question of, oh, okay, this is count, these are bits, I got to figure out to do the same thing. No, so like it reduces the cognitive load of reading this. Cool. Questions? Or actually, we can even look at the Verilog, I guess, if we're curious. And yeah, we can see, even though we said don't care, that's just us saying we don't care. The stuff's still concise and simple. There's no actual X's declared in here, but it comes through. Cool. Great. So we've shown this, valid interface and the couple interface in isolation. Let's go ahead and put them to work, right? And so what we're going to do is we're going to build a queue, right? So you can imagine if you have a producer and consumer, if you have this decoupled interface, you can, reliably send one thing or not send one thing. But what happens if, they're both bursty, right? Perhaps the producer sometimes has a lot of things to do, sometimes it doesn't have very many things to do. Likewise, sometimes the consumer has a lot to do, and sometimes there's not a lot of things to do. If you put a queue in there, this is a common architectural technique, right? You can use the queue to absorb, to smooth out the demand, right? So the whole point of the queue is that, if one end is really busy, it puts things onto the queue, the producer in particular, and then, as the consumer can get to them, it comes out of the queue. And what's nice about this is, if there's a short-term burst, the producer can still keep making progress. They can still keep putting things into the queue, and, things work out. Now, the key thing about queuing, and people often forget this, is that queues help with temporal variance. In other words, if you have a burst, it can hit that, absorb that, right? What queues do not help with is a fundamental throughput mismatch, right? If you simply are producing faster than you're consuming for prolonged periods of time, the queue cannot save you, right? The fact that the consuming throughput is lower than the producing rate is the freaking problem. But for momentary surges, having a queuing is really good. And the reason why we're talking about queuing today is that there's a queue in Chisel Standard Library, really helpful. It's a FIFO, right? But this FIFO, the way it talks to the outside world, is with this decoupled interface. This interface we just covered is, it's something handy in Chisel. You get access to a lot of stuff, right? And we know that behind the scenes, each of these decoupled interfaces is going to be, bits, ready, valid. So this queue is actually 6 different signals coming in and out of it, right? 3 for each side. But using decoupled is actually not quite as complicated as it sounds. Okay, so as I just showed in the prior slide, right, it kind of blows up into 6 signals, decoupled for both sides. But the nice part is, as we'll see in a second, the code is simpler than you think, and we can use those high-level primitives, things like .fire, to wrap up all the interactions with these things. Now, when it comes to actually declaring the queue, of course, you need to say what type is in there, and then how many elements. There is some additional arguments, pipe and flow, which I'll come to in a few minutes. We're going to ignore them for now. Okay, so you can see, right, the producer, is trying to send things into the queue, and the queue has things available to the consumer if the consumer is ready to take it. So you can see it kind of goes back and forth. If the queue has room, sure, it'll tell the producer it's ready to take more things. Likewise, if the consumer is ready to consume something, it'll tell the queue, I'm ready to consume, but only data moves here if both the consumer is ready to consume and the queue actually has data to send them, right? So these are all decoupled interfaces. Okay, so what's our example? In our example here, we're going to have a queue, or I should say a module wrapping around a queue. One syntax I'll point out if you haven't seen already, when you want to declare a chisel module for another module, actually instantiate another module, this is the style of syntax you need to do. It's a little bit counterintuitive. You'd probably think you could just do this, and it would be reasonable to think that. This is one of the cases where there's a little bit of boilerplate required because of Scala. But yeah, so you got to wrap it in a module saying I'm basically instantiating a module. It's not just enough to make the instance. You actually need to wrap it in a module. But once instantiated is fine. As you can see, we're going to go ahead and make this queue and we're going to connect it to things, right? In particular, we're going to connect this queue to a counter. So we're basically going to be counting into the queue when the queue is willing to accept it. And the queue's ability to ability to go outside the queue, well, it depends on what's outside, right? So you see that we have a few different decoupled interfaces, right? So there's one decoupled interface, which is the output of this entire module. For debugging, we also print out the count as well, make it invisible, but that's actually not really required. And then, yeah, basically the main thing is the enable. And yeah, inside this module, it's going to have a counter, and the counter is going to feed into this queue. How deep the queue is, that's a parameter. As I said before, we'll come back to pipe and flow in a few minutes. And of course, the counter is the maximum val. And because the queue has, decoupled interfaces, both input and output. Like I said, so the output of the queue, we connect to the output of this whole module. So that's easy. Now the input to the queue is also decoupled. That one we're doing more deliberately, right? You can see that one we are connecting to, .valid, .bits, etc. And then you may notice that io.enqueue.ready is not visible. And the reason why is we're using that in the context of fire right here. Okay, questions so far? There's a lot going on in this slide. Yes? It's not invisible, it's not shown, right? But .fire, if you see .fire, that's the same as saying, q.io.enqueue.ready and q.io.enqueue.valid. So the ready signal is set inside of queue in this case, right? So it's going to be very clear about which ready signal we're talking about, right? If we go back a slide, uh, I'm talking about this ready signal, right? There's another ready signal coming out. So our module is basically the first two blocks on the left are inside that module. Basically, the producer and the queue are in the box on the left. And then there's a unShown consumer on the right, which would be in our test bench. And so this ready is set by the test bench we're going to make in a second. It's the consumer. This ready comes from the queue, and the queue sets that. Like I said, you don't see that in this code because we're using .fire, but we could just as well have said, ready and, queue.io.enqueue.valid. But so .fire made that simpler, right? Like I said, at first you're like me, you're like, oh, reluctant to try these things out, but then you get into it and you realize, oh wait, this actually is simpler, it's easier. People understand what's going on. This is a decoupled interface. We're doing ready valid signaling. Yeah, okay, you get on board. Yes. So it depends on what kind of stuff you're doing. You can imagine like maybe if like the undergrad classes here, there's like CSC 100, maybe do something like, counting turkeys. So if you have that one project in that class where it's like, okay, there's turkeys going by your sensors. So you're counting things right now. It takes time perhaps to log that data. And so some of those things are bursty. You can imagine, especially like in networking, for example, like you're sending packets. Sure, there's real data. Sometimes you're not sending packets. There's no data to be sent. There's no demand, right? And so things kind of go burst in and out. Sure, that's another queue. Yeah, you have a write buffer and a processor. Yeah, there's a lot of things that have queues. Yeah, so you could have literally an entire course on queuing theory. But for us, this is a little bit about queuing, but mostly about decoupling, right? And so decoupling, just the nature that both sides have the ability to kind of pause the other side and not interact if they don't want to. And whether that's, a single thing outstanding, which is the original case, or if you have multiple things outstanding, if you have a queue, that's how you design things. So like you said, you can imagine a hardware design style where you have these high-level components that are all decoupled. They all have the ability to have queues that kind of arbitrate when they communicate and stuff. And that's a much more flexible design style. Now, earlier in the lecture, a question about something like AXI was asked. So yeah, you can imagine if you have IP blocks on your SoC talking via protocol like AXI. It's much more sophisticated than what we're talking about right now, but at a high level, that's a decoupled interface, right? If someone sends you an AXI command, you need to obey the AXI protocol, but you're not required to respond to them immediately, right? And so that's kind of thing. So AXI does kind of give you the same capability of having a decoupled interaction. It's just a lot more complicated, a lot more features. This is a very low level, bit-centric thing for perhaps smaller modules communicating rather than giant IP blocks. But yeah. Cool. Okay, so we set this thing up. We can go ahead and instantiate it, sure. And now let's go ahead and look at the output. So this test bench, I'm going to get a lot of mileage off, so I'm going to make sure to explain really clearly what's going on. 3 phases. First phase, we're going to be counting, but say the consumer is not ready. So as a result, all the numbers we count are going to go into the queue inside this module. In the second phase, we're going to disable the counting, but we're going to say the consumer is ready, and so numbers are going to be drained from the queue out of the module. And then the third phase, we're going to turn the counter back on, and we're going to be counting into the queue while draining from the queue at the same time. So there's kind of 3 different scenarios, right? First scenario, we are only going into the queue and not leaving the queue. Second scenario, we are not going into the queue, but only draining the queue. And in the first scenario, we are putting into the queue while draining. And to make things interesting, I have the counter's max value 1 greater than the queue size. So as a result, it's not going to be quite evenly divisible. So in the fill-up stage, for example, the counter counts 0, 1, 2, 3, no problem. If you look at what's coming out of the module, in the very first cycle, there's nothing in the queue, right? So if you ask what is the valid bit on what's coming out of this module, it's false because there's nothing coming out of the queue. It's in this cycle that the counter is putting the first value into the queue. And then from then onwards, the queue now has data. In particular, the queue has 0 ready to go. But because the consumer, which is, out.ready, is saying it's false, it's just filling up the queue and not leaving the queue. In the second phase, in the draining phase, right, we stop putting things into the queue, so we turn off the counter, but we say the output's ready to receive, right? So the result, you can see, oh yeah, it was valid, and this is true, so yeah, we, took something off the queue. Once the 0 is off the queue, of course, the 1 is next behind in the queue. that gets popped off as well. And then, after the one's popped off, the two gets popped off, etc. Now, what's interesting is because we made the queue only three deep, the count value is three and never made it into the queue. And so at this point, we've actually did 4 cycles of draining. There's nothing left in the queue, right? We did 4 cycles of trying to add, only 3 things winning. There's only room for 3 things in the queue. And then we did 4 cycles of draining, but there's only 3 things in the queue, so only 3 things came out. So this 3 kind of was, left in limbo. And then in the simultaneous mode, we start putting things into the queue. So at this point, the queue is empty, right? We start putting things into the queue, and it takes time for them to, takes a cycle to get into the queue, 1 cycle, and then cycle after that, it then comes out of the queue to the outputs. You see the 3 finally works its way through it, then the 0 and 1 is wrapped around. Okay. Questions on this? Yes. Oh yeah, good question. So even though it says 0, should some of these things be perceived as X? Definitely. So if you have a decoupled interface or a valid interface, more specifically, if it's not valid, it should not be, you should not be looking at data, right? If you're looking at data, if valid is not true, that means you're kind of cheating. You aren't really, you aren't really obeying the protocol. But as a good aside, I'll mention this for others on the recordings, people forget. Chisel, by default, even though there was that don't care annotation a few slides ago, for the most part, it's a two-state language, meaning values either 0 or 1 per bit. There's no X's or Z's really in the language. In simulation, you have things that are uninitialized. The simulators are designed to randomly pick values for wires or registers. So I think some people on the prior homework noticed, oh yeah, if I did or did not use reginit, things that did not work. Oh, sorry, that was lab 2, not the homework. Yeah, using reginit is usually a pretty good idea because that would make sure the registers and the value you know it's going to be. If you don't set the value intentionally, it could be an arbitrary value. Question, yes? Okay, this one does not. There is support in Chisel for a different structure to do clock domain crossings. And yeah, you have these, CDCs, clock domain crossings, async kind of FIFOs to get across them. Yes, that's another component inside the library. So Chisel will support multiple clock domains. I don't do it in this course, but yeah, that's out there and that's a common thing. Cool. Other questions? So now we're going to come back to these pipe and flow parameters, right? Actually, before we do that, we can go ahead and play with the other things. Instead of make the queue deeper, we see, oh yeah, we put 0, 1, 2, 3 in there. We can drain 0, 1, 2, 3. Everybody's happy. But no, it's more fun making it one smaller and watching the world, have to adapt. So let's talk about pipe and flow. So these are 2 additional features the queue has. And so I actually think I tend to find flow more intuitive. So I'm going to do that one first. So to get the idea of flow across, we fill up the queue. Oh, sorry, I need to, and it's backwards. We need to drain it. And then you notice how after I drained the queue, it took a cycle for me to get data into the queue before it could be taken out again. If you set flow to true, what this does is if your queue is empty and somebody is sending data to the queue and somebody's ready to receive from the queue, the data bypasses the queue and never gets written state. So it's a combinational bypass through your queue. And so you'll see down here, because of that combinational bypass, as soon as you turn on both the enables, both the enqueue is firing and the dequeue is ready, it's going to now become true, right? In other words, it's a combinational bypass path. So you're saying, wait a second. So let's talk about this, right? So this means that you have a queue, which was implemented as a FIFO of registers, right? And you're saying, the queue is empty, but someone's sending and someone's receiving. We can just bypass the queue combinationally. So there's certain implications for this, right? Depending on how our design is set up, this, could potentially become a critical path, which is why it's not the default behavior to turn it on. Potentially, I guess in some cases it can even be a combinational loop, maybe, I'm not sure. But like I said, there's reasons why you may not always want this on. But in the cases you do, this is nice, right? You save the cycle, right? And the cycle latency you cut out because, hey, why write to register and then read from register? If I know someone has data, someone's ready to receive it, just take it right away. So that's the flow parameter. Now the pipe parameter is similar, but not quite the same. So the pipe parameter is if I'm simultaneously enqueuing and dequeuing, what happens when the queue is full? Normally, if the queue is full, you cannot enqueue, right? Because it's full, right? Where is it going to go? However, if the queue is full and you're trying to enqueue and someone's also dequeuing at the same time, the capacity works out, right? Because they're going to take one thing off, you're going to put one thing in. And so if you don't have this optimization on, let's say I make the queue size 1. So what happens, right? Make the queue size 1, we put an element in the queue, take an element out of the queue, but coming into the final simultaneous phase, we have an empty queue of 1. So what happens? Well, we put an element in there, someone takes it, but because the one element went in there, the second cycle can't put another element in there because, oh wait, there's already something in the queue is full. And so you see as a result, data gets sent only half the time because, has to wait, fill up the queue, drain the queue, fill up the queue, drain the queue. So the pipeline parameter says, you know what? If someone's simultaneously enqueuing while someone's simultaneously dequeuing, we can enqueue while we're full because we know there will be space. And so you can see in this case, we now start sending data every cycle, right? Which is good. Now, this is only a corner case if you have one element. I just made it one element depth queue because that makes this more apparent. This comes anytime when you have all the elements full in your queue. It could be an 100 element queue full. The question is, do you need to wait for it to go down to 99 before you put something in there? Or fill it back up or not? And this is where that parameter comes in. Cool. Questions? Yes. It's a longer combinational path, right? Because if you go through the registers, right, the critical path is kind of whatever's in the, producer to get to the queue, and then whatever, is in the queue, and then whatever goes from the register to the consumer. If you have that combinational bypass path, essentially you now have a path that's through a portion of the producer, through the bypass path, and then through the consumer. So basically, you're now conjoining the producers and consumers' critical path, potentially. So it depends. It's not guaranteed to be a critical path. People use this. People do set this to true. But it's just to be aware of this, right? They are different mechanisms. So pipe controls whether or not you accept things even though you're full. Flow allows you to circumvent the entire queue if it's empty but someone's ready to receive and you're sending. And you can have them both be set to true, right? You can also, totally, make this thing awesome, spiff it up. But good questions. Yes. No, what's the point? The pilots do things when they're full if someone's also simultaneously going to take it. That's the key constraint. Yes. Uh, yeah. I mean, there's an analogy there. I think you're not wrong. I just think maybe it's easier just to say, yeah, let's do basically keep enqueuing when you're full, right? If someone's consuming. Yeah. So, I mean, internal to the queue, right? We aren't showing the internals of the queue. That'll be actually, I believe, Friday's lecture. Uh, I think so. Uh, you'll see that, there's different ways internally. And so sometimes you hold data shuffled down like a shift register for a queue. You can be more sophisticated and keep data in place. And so depending on how it's implemented, pipe and flow, the actual implementations under the hood could be very different than you're expecting. But conceptually, it's just, the pipe parameter is such that if your queue is full, you can still move data into and out of it in the same cycle if, you have both ascend and receive at the same time, right? Flow lets you bypass an empty queue if, someone's receiving. If someone's not receiving, guess what? It just goes into the empty queue, and now you have one element in your queue, right? Cool. Other questions? Well, no, I think that was a record fast lecture, but that's all, folks. Cool.